So whenever a TV cable is not coming, when he says help, you try to ring, then first you remove the connection and connect it again and check it. Right? So exactly same. Huh? So all right. So if you go to doctor and say that no, my eyes are not properly visible, remove it and then you can connect it. Okay. So the transconductance. Now what we have done is we have actually evaluated current by taking into account the channel length modulation effect. Actually, what I said earlier is current is equal to half mu Cx W by L dash into Vgs minus V threshold whole square. L dash is actually length is varying. It is a function of the VDS, but then VDS is not visible there. So what is there in your hand is VDS is varying, but length you cannot go inside the MOSFET and verify how much length it has varied. So therefore, what you have to do, is, because what you know is only the VDS. I am varying VDS. Current is varying. You just express as L dash, I can't do because I don't know what is L dash. Therefore, I should express it in known parameter. What known parameter? VDS, which I am changing. So therefore, I express ID in terms of the known parameter, right? As a lambda VDS, right? This is called channel length modulation coefficient lambda, right? All right. So similarly, once you know that current, then again dou ID by dou VGS you try to do and evaluate the GM accordingly. Okay. Now so far we thought that by when the applied voltage, gate voltage is less than the threshold voltage, the transistor is off actually. We are thinking, but in the beginning itself I said that for a given gate voltage, at least some of the electrons keep on traveling. Therefore, some amount of electrons will be there, and therefore there is a possibility of current. However small it is. So therefore, such current we call a sub-threshold conduction. When the applied gate voltage is less than threshold voltage, we call it sub-threshold. And if we try to model it, we will not go into the details, but then it is behaving in the exponential fashion. So therefore, the current ID is equal to I naught e power VGS by KT by Q. Okay. So we will not deal much about this, but one thing I can say that in the sub-threshold conduction also you can just use where the sub-threshold conduction will be useful is the question here. So if we try to look into actually very quickly look at the transconductance GM. So transconductance in the saturation. Transconductance is a mu Cx W into Vgs minus V threshold, and by looking at this, I want actually what I said, the larger the GM, the better it is, right? Because better sensitivity, gain is GM or not, therefore I will get better gain. Therefore I want to increase the GM. If I want to increase the GM, then what is the immediate thing that I will try to increase W by L. So probably I will go for larger GM. So if we try to increase W by L, then what is going to happen? If we increase W by L, what is the problem? If we increase W by L, right? W increases by keeping ID constant. Then I want to keep ID constant, but I want to increase W by L, right? So I want to increase W by L, but I want to keep ID constant. So try to look at the ID expression. ID is equal to half mu C X W L into Vgs minus V threshold whole square, right? So I want to increase W by L because I want to increase GM, right? But I want to keep the bias current to be same because power dissipation I don't want. So if I try to do that, then what should I do? What is the other variable? ID is equal to half mu C X W into Vgs minus V threshold whole square. W I am increasing, I am keeping ID constant. Therefore, this Vgs minus V threshold should decrease, right? So when V threshold is constant, so when I try to decrease VGS, then this fellow may try to approach V threshold, right? And if I try to further do it, it may go below V threshold, right? When they enter goes below V threshold, then it is a sub-threshold conduction. That is a sub-threshold conduction, right? So the simplest MOSFET, what happens is the device enters into the sub-threshold conduction, right? So therefore, what the bottom line here is that if you want to get larger transconductance, you try to increase W by L, all right? But then for the same ID, the device enters into the sub-threshold conduction. Even then you are happy, chalo, to kya hai. But the problem is, here what you are doing, you are increasing W by L, therefore the larger the W, the larger the size, the parasitic capacitance is more, and therefore RC time constant is more, which implies that it takes more time to charge and discharge to affect the changes. So therefore speed is at stake. Therefore you are thinking here, I am happy that I am getting larger gain, but the question here is the speed is very minimal. So these are the pros and cons about the subthreshold conduction. Therefore definitely we will go for subthreshold conduction, but the question when you are going to operate particularly under very low voltages, maybe energy harvesting, all these things, there we operate the transient subthreshold, but we have to see the speed is at stake. If you want larger speeds, probably it is difficult. So then this is the layout and all which you have been doing. Just I will not focus much about since I have some certain agenda I want to cover. Therefore let us try to quickly move on. The capacitance, MOSFET capacitance, very quickly let us try to look at the capacitances. Wherever there are two metal like things which are separated by dielectric, then there exists capacitance, right? So here you can see there, this is the gate and this is the drain, so there will be CGD. This is the gate and this is source, there will be CGS, and therefore similarly all many capacitances are there, right? So because of these capacitances now, also there will be, you can see there is overlap capacitance here and there is overlap capacitance here. So this is the overlap area, gate and source, gate and drain overlap area. So there is overlap capacitance, right? So you have to take into account all these all these capacitances when you are actually dealing with the circuit. Okay. So here you have to see the capacitance broadly can be thought of two types. One is oxide capacitance, another one is junction capacitance. Basically based on what is the insulation between the two plates. The insulation is oxide, then we say it is oxide, otherwise it is junction capacitance, right? So and the oxide related capacitance is basically the two overlap capacitances are fixed here, that is whatever the gate and drain, gate and the source, those are fixed here. The value is Cox multiplied by W into length is the overlap length, okay? And so gate channel capacitance, next one is gate channel capacitance. So the gate to bulk capacitance in the cutoff region CGB, but the gate and bulk, in the cutoff there is no channel at all, so between the gate and the bulk, so the capacitance is CGB, okay, CGB. So this gate to bulk capacitance is the Cox into W into L, okay? And in the linear or the saturation region there exists channel here, right? When the channel exists here in the linear region, we can assume that this is more or less it is channel exists uniformly almost there. So what we can do is this channel we refer it as we refer to both the source, see the capacitance between the gate and the channel, the capacitance between gate and channel. But once again the same story, gate and channel means how do you effectively measure it? Channel के अंदर घुसकर तो हम तो नाप नहीं कर सकते हैं, right? Therefore what you have to do, it should be referred to the two terminals, which is a source and drain. So when in the linear region the channel is existing uniformly along the length, and therefore we refer it equally to both the source and the drain. So therefore half into Cox into W into L for both the source and drain we refer. But in the saturation region it is not the case, because at the drain, the saturation region at the drain there is no channel at all, right? So therefore it CGD between the gate and the drain is 0, right? Only we refer to the gate and the source, and it is 2/3 of the Cox into W into L. So this is what is the capacitance, okay? So therefore we can just tabulate it in such a way that, so here for the cutoff region this is CGB Cox into W into L, and the linear region of course because there is no more connection to the bulk here, therefore they both are 0. And CGD is Cox into W into LD all the time, for every time throughout this will be there, because overlap is always constant here, and this is overlap is all the time there, plus half into Cox into L for linear region. For the saturation region it will be, where is saturation here? Saturation. For the saturation region this will be 0, right? So this is Cox into W into LD. What is this? CGD, okay? CGD is this one. And what is CGS here? CGS CGS in the linear region half CoxWL plus CoxW into LD, and CGS is 2/3 CoxW into L plus CoxW into LD. Is it okay? So there's no big deal here. One thing you have to remember is the gate to channel capacitance is referred to source and drain, whose value is half into Cox into W into L for both gate source and gate drain, and for the saturation region it is gate and drain, it is 0, gate and source it is 2/3 of Cox W into L. Alright, so let us move ahead, and not only that, there will be sidewall capacitance also will be there, sidewall capacitance also will be there. So these are various channels are there, various junctions are there. So this is the first junction is what this is N plus, this is N plus here, and this is P, N plus P junction, and second one is this is N plus and this is P, the N plus, the second one is N plus and P plus, because all the three sides we try to put channel channel stop implantation will be there. So we try to clad with the P plus all the three sides, so that unnecessarily there will not be any current flowing to the adjacent MOSFET. So therefore through all the three sides there will be P plus channel stop implantation. So therefore here all the three sides external to the substrate there will be what you call P plus implantation. Therefore this is here this side it is N plus and this side it is P plus, N plus P plus junction, and whereas this one is also N plus P plus junction, right? And how about this fourth one? Fourth one is also, this is N plus and this side it is P plus, right? And the fifth one is bottom plate. Bottom plate is, this is N plus and is below this what is there? It is substrate P. So therefore it is N plus P junction, N plus P junction. So these are the various junctions, because whenever there is P-N junction based on the doping and all, the corresponding P-N junctions you have to take into account, right? So this all I just mentioned. I will not go much into details of that. Okay. So now we will try to we'll quickly move into small signal model. Okay, the small signal model, let's try to just look at it is how do we model the MOSFET here? It's by varying the gate voltage, current is varying. By varying the gate voltage, current is varying. So how can I view it? It is just like a voltage dependent current source. It's giving me almost, see in the saturation we are thinking that current is constant, ignoring the channel the modulation. So it is a current source. Which type of current source it is? Voltage dependent current source, because by varying the gate voltage, it is voltage dependent current source. So therefore it is represented by voltage dependent current source. And what is it? GM VGS. Why? Because the current is varying. It is dou ID by dou VGS is GM. So therefore the magnitude of the current is GM VGS, right? Dou ID by dou VGS into VGS is a ID, right? Therefore GM VGS. And then this is the gate, this is the source, therefore I am applying voltage here VGS. This is small signal model. Okay. Now what is the R0 for this? So if you want to evaluate R0, dou VDS by dou ID, I want to evaluate. Dou VDS by dou ID is 1 by dou ID by dou VDS. I know current expression, try to just now using the channel the modulation and all. So do that, simply you will get 1 by lambda. If you do that you will get it. I am not spending time here. 1 by lambda ID is the resistance. Okay. So now, but I have to take that also into account. Because in this case we are ignoring the channeling the modulation. So by the virtue of channeling the modulation, if you ignore the channeling the modulation, R0 is infinite, because dou ID by dou VDS is, there is no change in delta in the current with respect to VDS. Therefore dou ID by dou VDS is infinite. The delta ID is 0 with respect to VDS, right? So therefore dou VDS by dou ID is infinite. Dou ID by dou VDS is 0. Dou VDS by dou ID is infinite. R0 is dou VDS by dou ID, which is dou VDS by dou ID is infinite. So we are not, I am not putting anything here. But there is a change by the virtue of channeling the modulation. Therefore I have to represent that also as a function of. So how do I represent? It's just like alpha VDS or whatever. So I can replace also another voltage dependent current source, but then to make our life easier, we will replace this with a resistance, because the slope, that variation not that much. Therefore I can say it's just like a resistance. So that variation I will replace it by value R0. I will replace it by R0, whose value is 1 by lambda ID. Okay. So therefore equivalent. So in the other one is there we ignored the bulk effect. So current is also varying with respect to VBS. That is another voltage dependent current source. Another voltage dependent current source, dou ID by dou VBS. That also you have to take into account. Therefore, dou ID by dou VBS you have to just calculate it here. This is current expression, but then where it varies actually the threshold voltage, right? Because threshold voltage varies with respect to VBS. We have seen that, right? So I just now do a little bit of math, then say I will get GMB as this one. Okay. So finally, your small signal equivalent circuit is just like this. So what you can see here is this is a voltage dependent current source GMVGS, R0 due to channel length modulation, GMBVGS towards the body bias effect, because current is also a function of VBS. Okay. Well, this is the final small signal equivalent circuit. Okay. So let's try to move very quickly. This is actually capacitance varies. Let's try to, I'm eager to move towards it, but then let's try to, if you want. Okay, so how do we see MOSFET as a capacitor? How do we see MOSFET as a capacitor? Very quickly, let's try to look at how to view the MOSFET as a capacitor. So capacitor is a two-terminal device, right? So MOSFET we have three terminals. What we'll do, the source, drain, bulk of the MOSFET are grounded here, right? Source, drain, bulk, तीनों को ground. What is left over? So it is now between the gate and ground. That's all, right? So gate is there, and all the other three terminals are other terminal, one terminal. So there are the two terminals. One is gate, other one is all the three terminals put together. Now it is a two-terminal device. It's a two-terminal device, right? So what is there in between? In between, silicon dioxide is there. Therefore, some insulator is there. I can view it as a capacitor, right? Because polysilicon is a metal-like, and then below it is a semiconductor, and then in between, what is there? Silicon dioxide, right? Therefore, let's say to sometimes when you want to analyze for very deeply, then you have to put double jet. So and later veins. Okay. So the transistor therefore can be considered as a two-terminal device. Okay. So what you are doing initially, I'll try to put vary the gate voltage with a negative voltage. So the gate voltage is varying negatively, right? When VG is less than 0. When VG is less than 0, then what happens here? The less than 0 negative voltage is applied, right? So all the holes get attracted towards, holes are getting attracted towards the oxide silicon, right? So therefore this is called accumulation region. This is called accumulation region. Okay. So now as VGS rises, what happens? As VGS rises, the density of the holes at the interface is going to fall. So as VGS is going to rise, what is going to happen? So the holes, because now I am making it more, first it's negative I said, so holes have come up. Now gradually from negative, gradually it is coming towards 0 and it is becoming positive. So what happens? The holes get repelled. The holes get repelled. Gradually the amount of the holes first reduces, accumulation to khatam ho jayega, right? And then what happens? Depletion region forms, right? So therefore the device enters into the weak inversion first. Okay. So as gradually all the holes have gone, then what happens to capacitance here? You know that capacitance is epsilon naught A by D. D is Tox separation. So what happened earlier? So only Tox is the separation. Only Tox is the separation. Epsilon naught A by, this is the distance Tox, right? Oxide thickness. I got some capacitance value. Now what is happening? As I am making this gradually from negative towards positive, these accumulated holes have gone, right? But then what happens? It causes a depletion region will be formed. So depletion region, hey, this is crying. It needs charge. now effectively what is separation? This oxide is one insulation and other one is the depletion layer also. Depletion layer. So what is effectively what is separation between the metal which is a polysilicon and the other metal type, let's say it is silicon. So between these two, what is the separation increase or decrease? Increase. So when they increase, what happens to capacitance? The capacitance should decrease. Capacitance decrease. So right, therefore capacitance keeps on decreasing. Okay. So therefore the capacitance keeps on decreasing. Right? But the moment the applied voltage is greater than the threshold voltage, then what happens? The depletion region is now exhausted, and then all the electrons in the place where layer holes are there, the electrons go on accumulating. Right? Therefore, that is a complete question here. Right? So now what happens again? The distance decrease. So what should happen to capacitance? Decrease. So that's what it is. Right? So the capacitance now. Now we can see that simple MOSFET is a regulated capacitor, and I can always have capacitance of my value by choosing appropriate W value, because the capacitance value is a function of the area. C ox into W into L. Larger the WL, the larger the capacitance. Therefore, I have beautiful capacitance in my hand. So I can realize now we are in a position now. We got a small signal amplifier. A simple is a common source amplifier. For the sake of simplicity, we are trying to connect that an ideal current source. Now, what I am going to do? DID is, I know the current MOSFET is a function of two various voltages. What are they? One is so current is a function of, therefore DID small change in the current is a function of dVg and also the function of dVg. Therefore, dou by dou dVg plus dou by dou dVg. So by definition here, I can write that dou ID by dou Vg is equal to G. Right? So, and dou ID by dou Vd is G. So, dou Vd by dou ID is R. Okay. So, this is a reciprocal of that is G. So, we can write the differences here. Now, what I can do, so, but I know since I consider constant source, so DID is equal to 0, I will start writing the equation. DID is equal to 0, 0 is equal to, now, whatever the earlier I put there, dVd and all, I am trying to replace it by small, I am trying to replace it by, this is dou ID by dou Vg Gm, this is Gm, and this dVg, I write small letters, Vg. Vg is actually Vi. Yes. And this is a G naught, and this is V naught, small. Okay. So, if I want to evaluate the gain, what I will do? Gain is equal to V naught by gain. Right? So, it is basically take these two things, either this and that set, and then V naught by V is equal to minus Gm by G naught or minus G naught. And so I can write, don't read too much into these equations, which I have already seen. So this is ultimately gain expression, and current is half UC of square. Other parameters are simply taken on. Okay. So we always see that the Gm can be expressed in three different ways as a current batch, voltage batch. So now, if you want to evaluate, if you're interested in evaluating the gain in all the three modes, I said voltage batch, current batch, so technology. In all the three types, probably you can evaluate the gain. But evaluate the gain, then you should know what is Gm in all the three modes, right? And also you should know what is R naught in all the three modes, or P naught in all the three modes. So for which case, what we will do? So this is a all the three modes that evaluate the what we call Gm G naught and then decay. Okay. So this is G naught is equal to, already we have seen that is 1 by lambda I, right? This is exactly the same, and G naught in all 3 modes, this is 1 mode, this one here, and so for example this is calculated in the voltage balance mode, and so this is gain in the voltage balance mode, right? Therefore, similarly, if you can evaluate in the current balance mode, in math if you do, we will discuss. There's no point in doing math here. I'm just taking that. So see, what is the way to do? We calculate G naught. How G is calculated in G is expressed in terms of what is it? Voltage balance mode, the current balance and the current balance. And therefore, in the current voltage balance mode, Gm is there, G naught is there, multiply Gm G naught, you get K. Same is the case for the other two modes. When you try to do that, in the current balance, you find that the gain is proportional to the square root of the area. Square root of the area. Okay. Okay, so now what we are going to do is try to apply KCL. This is what we reference. So far what we have done? So far what we have done is we have ignored the capacitances and simply we are calculating GMR now we have. This is not the case. There are capacitances existing, therefore you have to take the constant here. So what are those capacitances here? The capacitances are the gate and source, this capacity, the gate and drain, this capacity. So here are this capacity, right? So apply KCL here. Apply KCL now, you do this math from the beginning. I'm trying to go faster. So this is a VI. This is VI, this is V0, right? So VI minus V0 divided by 1 by CGDS. Okay, that is that becomes a CGDS into VI minus V0. This is one current here, right? And the leading current here is GMVI, so minus GMVI. And what else? The other leading current is V0 divided by R0 and V0 divided by 1 by S C0. Okay, so if you solve, you will get gain as this. So you can also verify that at 0 frequency SC is equal to j omega, right? So omega is 0, simply this all will go and minus GM or not, right? So I can write my gain as in terms of C total. This is what is the gain here, and that is A naught into the GM naught is A naught. I have put here. I will try to express this way. Okay. Now what I would like to just make an assumption is that this omega CGD is far for the frequencies omega CGD by GM is far less than 1, right? That is not I am not doing any violation here. What I am trying to do is omega CGD by GM is far less than 1. That is what I am just because GM is pretty larger generally. GM is larger, and I am trying to consider those frequencies for which omega into CGD by GM is far less than 1. Generally it is the case, whatever is because I said GM is pretty large and CGD is of the order of the femtofarads. So already of the order of femtofarads and divided by large GM try to put here. Therefore I try to get here that value will definitely be small far less than 1. So I can just now ignore for those frequencies, and then this is approximately equal to this here. So therefore gain bandwidth, this is the gain here, and the gain bandwidth product if you want to evaluate, because this is the gain, and this multiplied by gain bandwidth product, right? So before we go to that, please try to see that this describes the frequency response of a system with one dominant pole. There is only one dominant pole. What is that pole here? The pole is if you want to evaluate, omega is equal to 1 by R naught C total, right? 1 by 2 by R naught C total, right? So therefore the bandwidth is given by 1 by R naught C total, and the gain bandwidth product if you want to evaluate, gain is GM R naught multiplied by bandwidth 1 by R naught C total, so which is simply GM by C total, right? So what is this? This is what is gain bandwidth, in this is unity gain frequency. This is the frequency for which the gain falls to unity, right? Or the gain output becomes equal to input here, right? So This is what is the gain bandwidth product here. So as frequency increases, this becomes unity. Okay. Well. Okay. So now, so the maximum possible cutoff frequency occurs for an unloaded amplifier, because C total keeps on increasing when you try to add more and more load, right. So C total is equal to obviously how can I write here, there where the capacitive load is entirely due to the device capacitance itself. So therefore C total is a function of the device capacitance is proportion to W. Right. So therefore I will write GBW maximum is equal to GM by C total. I said in the place of C total I am writing it as the function of W, some zeta into W. Okay. Now GBW maximum you can also calculate as K dash VGT by, this is for all the three styles you can calculate, for all the three styles you can calculate. Please make a note of this slide. You have to change the equation numbers, all these things you have to remove it. So this all is the for all the three different styles, this is what is the GBW. Okay. Here you can tabulate all this, you can tabulate all whatever for all the three styles, right. What are the three styles? Voltage base. The voltage base, the free design variables are W, L and VGT, and for the current base WL ID, and for the other base it's L, VGT and ID. You can calculate GM, G0, A0, GBW and GBW maximum, whatever it is. Right. So now what is that, why we have plotted all, why we have actually tabulated all this is the question here. So one important observation we try to draw here. So if you want to evaluate the gain multiplied by GBW maximum, right, then you can find that it is ultimately gain into GBW maximum is some 2K dash by alpha, all this, right. Don't read too much into all the what is a lambda, all this is just a function of technology parameters. So the observation is that nowhere your there's no, it's not a function of the voltage, it's not a function of the current, it is not the function of W or L, whatever. That means that when you try to evaluate the gain and GBW maximum product, this is fixed for this topology. If I want to improve it, I can't do it. Nothing is there in my hand. Voltage is not there, current is not there, W is not there, L is not there, right. Therefore, what it implies is, if I try to increase, if I want to improve this performance of this topology, I can't. I am pushed to wall. I am pushed to wall. Therefore, the only way which is left with me is change the technology, right? Or otherwise go for another topology. For this topology, common source, I can't do anything more. Not only that, in the common source amplifier, you can just now also see in the common source amplifier, you can also see that between the gate and the drain there is CGD is there, right. This capacitance CGD, right. Now where you are taking output here, I am trying to take output here and this is the input, but the output and the input there is an impedance which is in terms of capacitance here. Try to recall the Miller theorem. In an amplifier when there is an impedance between the output and the input here, that can be replaced by how? At the input, I will remove this feedback. At the input, it can be seen as it can be seen as, if the impedance is Z here, then it is seen as Z by 1 minus AV. Z by 1 minus AV. So when Z is here, what? 1 by CS, 1 by CGD. So 1 by CGD. So 1 by CGD. So this is the Z which is connected between the output and the input here. So that can be written as Z by 1 minus AV. So Z is equal to 1 by CS or CGDS, okay, into 1 minus AV. 1 is small as compared to voltage gain, so it is AV, right. It appears that the CGD is multiplied by gain times and is appearing at the input, right. So that is actually, that may cause the frequency response to be hampered. So what that means is, if I try to this is the voltage gain and this is the frequency, right? If I try to increase the gain, right? So what is happening? This capacitance which is it's encountering seems to be large, right? So therefore the corresponding pole moves towards the origin, right? So I can say that this unity gain frequency is coming closer to the origin. So available this gain bandwidth is decreasing, right? So larger the gain, the smaller the bandwidth it is, right? So therefore for this given technology I can't improve anymore. Now I want to see that for the same unity gain bandwidth, that is earlier it is like this, right? So this is here, I want to go here, then it is. But if I want to increase the gain, but I don't want to change this unity gain frequency. For the same unity gain frequency, I want to get a larger gain. Then what should I do? That is, I want to get a larger gain here. So for the same unity gain frequency, I want to have this. Okay, I want to get a larger gain for the same unity gain frequency. I can't do anything here, but I should think of a solution. So whenever there is a problem, then if you want to look at the solution, then immediately what we have to look at is who is the culprit, who is causing the problem, right? Who is the culprit and who is causing the problem? Who is the culprit? The culprit is this fellow. This capacitance is between the output and the input. The capacitance CGD is there, right? So that fellow due to Miller, it is getting multiplied by gain terms actually. The larger the gain, the larger you are increasing W, and therefore the larger the C, and therefore actually C is getting even multiplied by gain terms. So therefore what is to be done is since between the output and the input the capacitance is there, so somehow you have to resolve it. So probably if you don't take the output from here, take somewhere else here and isolate, that is isolate the output node and the input node. Isolate the output node and the input node. Isolation in the sense who will come to our rescue in the MOSFET technology or the circuits here. No one else come to our rescue, only another MOSFET only will come to our rescue, right? So therefore what I will do, I will use another MOSFET and I will try to isolate what? I will try to isolate output and the input node, right? Because output and input node, if I am taking output here, then this CGD is between the output and input, it is there. I will not take output here, I will try to put another MOSFET here and try to take output from here, right? Then I am successful in isolating the input and the output node, right? So this is what exactly I can see, that I have isolated the output node from the input node by connecting another MOSFET. This is the cascode topology. So I am trying to get rid of the Miller effect, and therefore I want to improve the performance. Okay. So here you can analyze once again. Okay. So remember these two transistors are in series, therefore current through both of them are same, right? We will analyze it with a small assumption. Let us assume that there is a fictitious transistor, because here what is happening, please remember, here signal is applied here only. Here I am giving only DC. Okay. Therefore I can view this as a single transistor, a fictitious transistor, ఊహాజనిత transistor, which is taking input from the gate of this is called driving transistor, because this fellow is being driven by the input signal. This fellow is not driven by input signal, but there is what is this voltage? DC voltage. This is a DC voltage to keep this in saturation. Okay. Okay. So therefore this is a DC voltage, all right. Now what we would like to see here is when you try to treat this as a single fictitious transistor, and input voltage is from at the driving transistor and output is being taken here. Okay. So, this is single transistor. Now, dou ID by dou Vg1 is going to give me the transconductance of that single transistor, GM effective we call. This is for the, not for the this transistor, this is for the circuit. The circuit is viewed as if a single transistor, input here, output there. Dou ID by dou Vg1 is the effective transconductance, GM effective. Similarly, dou ID by dou Vd2 is the effective conductance, G0. Okay. Well, so again same story. This is dId is any current is a function of what? Transconductance, as a function of the gate voltage and the drain voltage. I am viewing these two as a compound transistor where input is being taken from Vg1, therefore it is Gm equivalent into dVg1 plus G0 equivalent into dVd2. Right? Now, Gm equivalent is equal to dou ID by dou Vg1, but by dVd2 is equal to 0, because I want to see the variation in the current only due to the variation in the Vg1. So, Vd2 I am trying to mute it. Right. Similarly, G0 equivalent if I want to calculate dou ID by dou Vd2 when dVg1 is 0. Right. So, therefore, I can now write dVds2 is equal to dVd2 minus dVs2. Vd2, I know that the source of this fellow, see this source of this transistor is the same as the drain of this transistor. So, Vs2 is equal to Vd1, Vs2 is equal to Vd1. Am I right or not? Huh? Am I right or not? Vs2, this is transistor M2. Vs2 is same as Vd1. Not convinced. This is the source. S2 and D1 are connected together. S2 and D1 are connected together. So, obviously Vs2 is equal is same as Vd1. Vs2 is same as so Vs2 is same as Vd1, and same as again what is the why actually what is this 0 here, because dVd2 minus dVs2, right? dVd2 we have made it as 0. Why dVd2 is made as 0? Because we want to calculate GM effective. When we calculate GM effective, what are we doing? dVd is 0, only variation due to the voltage at the gate, the current is only due to the applied voltage at the gate of the M1. So, therefore, this is 0. Now, dVgs2 is equal to dVg2 minus dVs2, but dVg2 is also 0. Why dVg2 is 0? Why dVg2 is 0? dVg2 is 0 because you are right, you are there. What is your name? What is your name? Rishi? Trisha. Okay. Good. Even if it is winter, you are working. Actually, you are supposed to work only during rainy season. So, this is, you are right. Tell me, you are right. It is the DC voltage. It is not difference, it is a DC voltage. The DC voltage, therefore, signal I am not applying there. Therefore, delta change whatever 0. There won't be any change there. Am I right or not? So, this is dVg2 is or small vg2, it is 0. Right? All the time it is 0. All the time it is 0. Right? So, therefore, this is 0 minus dVs2. dVs2 is again dVd1, right. So, let us say to move ahead, we will try to make use of this and substitute here, and so ID, now what I will do is, I will go back, I will try to write the current equation for both the transistors separately. Transistor M1 I'll try to consider. Any transistor for any transistor, current is a function of what? Gate voltage and drain voltage. So therefore, ID is equal to GM1 VG1 plus G01 VD1 for any M1. For M2 it is GM2 VG2 plus G02 VD2. So GM2 VGS2. What is VGS2? VG2 minus VS2. VG2 is 0, 0 minus VS2, VS2 is VD1. So therefore minus VD1. Therefore it is minus GM2 VD1 minus G02, actually this is a plus G02 VD2. When the G02 VD2 VDS2, what is VDS2? dVd2 minus dVs2, but dVd2 is 0 because we are calculating GM effective. We have made it as 0. So it says dVd2 is 0, so it is only minus dVs2. But dVs2 is again dVd1. Therefore it is minus dVd1. Therefore this is okay. Now equate both of them and then we'll get Vd1 is equal to minus ID by Gm2 plus G02. Right. You got that, and then one thing you have to just know, keep in mind, right? So what is that? The gate to source voltage of the transistor is going to change here as the drain voltage of the lower transistor goes up. The value of the gate to source voltage of the upper transistor is going to reduce, reducing its current, right? So if you want, try to look at this circuit, then only you will understand. So what is happening here? What is happening here? Actually both the transistors are in series. Both the transistors are in series. Here only I am applying signal. So in response to the application of the signal or variation signal, the current has to vary, and the same variation should reflect through transistor M2. Right. In proportion to what? In proportion to change in the input signal voltage. Right? Is it okay? But the question here is, what is happening? When this current is changing and all, due to one or other reason, if this voltage changes, Vd1 changes, right? If this voltage changes, then what happens? For example, this voltage goes up. This voltage goes up. When this voltage goes up, what happens to this VGS? What happens to VGS? VG is fixed. This voltage is increasing. What happens to this VGS to? Decrease. VGS to decrease, the current has to decrease. The current has to decrease. But we are thinking that the current is only a function of this V in. This fellow is changing, then the current has to change. But due to, suppose this voltage is changing, something dropped here and rest of the things are being dropped here, therefore this voltage also changes. When that is happening, then, and the change is in such a way that this voltage is increasing, then what is happening? This fellow is decreasing, VGS2 is decreasing. As VGS2 decreases, the current is decreasing. So हमारी बात मान नहीं रहा है in total. To some extent, applied gate voltage accordingly current is changing, but what happened is this current change now is not just the function of this V in, rather you can find that there is some slight reduction in the current by the virtue of the variation of this voltage. This is a sort of feedback that you can think of, right? So what is the hint that you will get here is, earlier we thought the current is only a function of variation of this, therefore for this entire circuit what will be the GM effective? If you have to see, GM effective is approximately equal to GM1 only, because this fellow same current is forcing to flow through this, therefore total GM for this circuit should be same as of this transistor. But what is happening now? It is becoming slightly less here, because this fellow is causing to vary this voltage, and therefore this GM is a decreasing, right? Not only that, also you can see this transistor, the bulk of this transistor is at ground, source is not at ground. Therefore, there exists a body bias effect. There exists a body bias effect. Because of the body bias effect, now as the source voltage of this transistor is going to change, or drain voltage of this transistor, suppose it increases, then what happens? VBS becomes more negative. When VBS becomes more negative, then threshold voltage of this becomes more. When threshold becomes more, current becomes less. So again same story. So the current is not dancing to the tune of the input signal voltage, but some portion of the current variation is also internally, it is a different, right, which implies that the transconductance GM of this entire circuit is not exactly same as GM1. It is slightly less than the GM1. Mathematically also we can see that, right. I have given the reasons, and then now we will try to see mathematically. So now you try to calculate it. How do you calculate it? So ID is equal to GM1. Now we have seen those two equations, right, from the these two transistors here, right. VD1 is equal to minus ID by GM2 plus G02, right. So this we will try to take and try to substitute here in this, okay. So I will try to do that. So ID is equal to GM1 VG1 minus ID into, I will try to substitute this. Is it okay or not? See what I have done from here. I have calculated VD1 is equal to ID by minus ID by GM2 plus G02 from this, right. Okay. So this I will try to go and substitute in the place of the VD1. In the place of VD1, I will try to substitute here. Is it okay? So when I try to substitute there, then this becomes, it is this, and just simplify, and then you will get this is a GM equivalent is what? ID by VG1, ID by VG1, right, is equal to, I will get this expression. So what did you get here? GM1 into GM2 plus G02 by G01 plus G02 into GM2, which implies that GM equivalent is slightly less than GM1, because denominator is greater than numerator. What are the reasons? Conceptually we have already seen. GM effective is less than GM1. Okay. Now if you ignore, because GM is generally greater than G01 G02, if you ignore this, right, and if you ignore this fellow also, then simply it is approximately equal to GM1. Approximately GM1, exactly less than GM1. Okay, right. So now we have calculated equivalent transconductance. You want to calculate equivalent G0, right. How do you calculate equivalent G0? So G0 equivalent is equal to dou ID by dou VD2, right. So with dVG1 is equal to 0, right. So what is dVGS2? dVGS2 is dVG2 minus dVS2. dVG2 is 0, dVG2 is all the time 0, and so minus dVS2. But what is VS2? VS2 is same as VD1, right. So it is minus dVD1, right. And what is dVDS2? dVDS2 is equal to dVD2 minus dVS2, right. So dVD2 minus dVS2, VS2 is VD1, right. So dVD2 minus dVS1. Okay. Now, so is it okay? Huh? Any doubt? Should I repeat? So what we are trying to do is G0 equivalent is equal to dou ID by dou VD2. Dou ID by, as a single unit, dou ID by dou VD2. Dou ID by dou VD2 at this node. See impedance in looking into it. Dou ID by dou VD2 with this fellow is 0. If this is also there, I can't exactly tell that this current variation is only due to the variation of this voltage. So I will mute this when the current is a function of two voltages, and I want to evaluate the variation of the current only due to one voltage. I have to mute. So this fellow is muted. So therefore this becomes dou ID by dou VD2. Dou ID by dou VD2 with dVg1 is equal to 0. This Vg1, right? This fellow is 0. Now I am just writing expressions. dVgs2 is equal to, what is dVgs2? dVgs2 is dVg2 minus dVs2, Vs2, right? dVg2 is 0, so it is minus dVd1. Why? Because Vs2 is same as Vd1. And what is dVds2? dVds2 is dVd2 minus dVs2, dVd2 minus dVs2. So dVs2 is same as dVd1. So it is dVd2 minus dVd1. We should not get confused. Earlier we made dVd2 is 0. Now also no. Earlier for the calculation of GM effective, we made dVd2 is equal to 0. We made dVd2 0 for the calculation of GM effective. Here what is that you are assuming? dVg1 is 0. Right? So this one. Now ID is equal to for both the transistors I would like to write. Okay. So what is the current now ID? It is transistor M1. I will write it as GM1 Vg1 plus G01 Vd1. Right. GM1 Vg, I am writing for this transistor separately. GM1 Vg1 plus GM2 Vd2. Right? No. For transistor M1 I am going to write. Transistor M1, it is GM1 Vg1 plus G01 Vd1. G01 for transistor M1 only I am writing. So GM1 Vg1 plus G01 Vd1. But GM1 Vg1 is 0 because I am calculating this fellow. So Vg1 is 0. So dVg1 or small Vg1 are the same. Therefore this fellow is 0. ID is equal to G01 Vd1. Right. So and from here what is Vd1? Vd1 is equal to minus ID by minus ID. ID by G01. Very good. ID by G01. So all of you are not sleeping. Now ID is equal to now what I will do, I am trying to take the transistor M2. Transistor M2, what is ID? ID is equal to GM2 Vg2 plus G02 Vd2. Excellent. So GM2 VDS2 I should write. GM2 VDS2. Earlier we are not pronouncing S because it is already ground. But this is not at ground, so I have to write GM2 VDS2 plus G02 VDS2. So GM2 ठीक है, VDS2 is already we have written. So VDS2 is VD2 minus VS2, but VD2, so this is dVD2 minus, in the place of VS2 it is VD1. VS2 is VD1. So therefore this fellow here I am trying to write here. So minus GM2. So what is this expression here? This is now GM2 into this is VGS2, right? VGS2 is VG2 minus VS2. VG2 minus VS2. VG2 is all the time 0. That's what I am telling. VG2 is all the time 0. I am expanding, that's all. For this transistor, all the time VG2 is all the time it is DC only. For the upper I am not giving any signal. Signal is being given over to the bottom transistor. Now that also I am not giving. Don't think that earlier I have given to bottom transistor, now I am given to upper transistor. नहीं कर रहे हैं भाई. Not that. See, upper, yeah, you see upper transistor in this sense. In the signal, this is signal is earlier we have given here. now we are muting this, but here this voltage now you are considering, this voltage variation you are considering, but this voltage all the time is DC. Where output impedance means what? Dou VD2 by dou ID. So variation is at the drain node of the upper transistor. dVD2 by dou ID, dID. Understand? Not this gate voltage. Gate voltage is all the time DC I am giving to keep that in saturation. So therefore this is a GM2 VGS2 when you try to calculate, GM2 into VZ2 minus VS2. VZ2 is how much? 0. VS2 is VD1. So therefore it is minus GM2 into plus G02 into VDS2. VDS2 is VD2 minus VS2, VS2 is VD1. Is it okay? Right. So, any doubt? Now, just it's a matter of solving this, that's all, right? So, from here, I am trying to write ID is equal to, what I am trying to do? I am going to substitute here, what I am going to substitute here? So, from here, so ID is equal to, substitute whatever is the VD1 there. So, just to solve this, I will get, say with G0 equivalent is equal to ID by VD2 if you solve, I will get this as the. So, here once again GM is larger than these two, therefore you can ignore this, then this becomes G01 into G02 by GM2, or R0 equivalent is equal to ulta karo GM2 by G01 G02 or GM2 R02 into R01. GM2 R0 equivalent is equal to GM2 R02 into R01. What does it mean? It means that when a single transistor was used, the output impedance was R0 or R01. Now it is impedance seen will be GM2 R02 times R01, right? So the output impedance is enhanced by a gain factor GM2 R02 times R01. It's a big boost in the output impedance. It's a big change in the output impedance. Is it okay? So output impedance is increased by a gain factor. Okay. So now you can calculate what is the gain. You want to calculate the gain here. So gain is equal to minus GM equivalent divided by G0 equivalent. So the gain is minus GM equivalent by G0 equivalent. So already you calculated GM equivalent and G0 equivalent, just substitute there. You will get this is the expression for the gain. Okay. Again, what is the observation here? Observation is this gain is corresponding to the common source amplifier. Yeah, I just have to mention you that this cascode is a combination of, this is a common source. Source is common between the input and the output, and this is this is a gate is a small signal ground because DC is not, only DC is there. So therefore where it is taking input? It taking input at the source and it is delivering output at the drain. So what is common between the output and the input? Gate. So it is a common gate. So a combination of common source is the cascode. So the gain for this fellow is GM0. Okay. So that is GM1 by G01 or GM1 R01, and for the common gate amplifier this is the gain. So overall gain is A01 into A02. Okay. So this is what the DC gain, this is what the DC gain, and you can also see that this gain actually, if you ignore this fact, if you ignore this one, then if you try to multiply GM, if you assume that GM1 is equal to GM2, G01 is equal to G02, then both are equal to GM1 is equal to GM2 is equal to GM, G01 is equal to G02 is equal to G0, then the gain will be GM R naught whole square. If you ignore this, it becomes GM R naught whole square. So see that in the cascode, the gain is improved by leaps and bounds. GM R naught square, so a huge improvement in the gain, right? This is DC gain, huge improvement because we have not considered the capacitances, not included capacitance, right? Now I will try to consider the capacitance also. So when I try to consider the capacitances, these are the capacitances, CG1, CGD1, all these things, right? But how did I draw this small signal equivalent circuit is the question. So for the first transistor, it is no issue here. This is the gate, this is the source. So between the and what is this? This is the, see, this is the gate, I said, right? Gate, and this is the drain, right? So between the gate and drain, CGD is there, and drain and the source is ground. So there is a voltage dependent current source, GMVGS, whatever it is, and R01 parallel. Till this no problem at all. But then here comes the second transistor. How do you put this small signal equivalent circuit? The question for the second transistor, okay. Second transistor, where is the source of the second transistor? Leda కొంచెం పైకి చేయండి. ఇంకొంచెం పైకి బస్. Okay, thank you. Where is the source of the second transistor? So this is a S2 and this is a D1, right? So if you try to plot, this is what is my G1 and this is my D1. This is voltage dependent current source, and there is a capacitance here, right? And there is a capacitance here, and this is resistance R01. Now for the transistor M2, this gate G2 is a small signal ground. Gate G2 is at a small signal ground. So gate is a small signal ground, and D1 and S2 are connected. So D1 and this should be S2. D1 and S2 are connected. Don't move away from the frame. D1 and so your identity card is valid till tomorrow. Okay. So D1 and S2 are connected. Okay. And where is my D2? So this is a D2 here. So between the D2 and S2, I have to write what? The voltage dependent current source. For a MOSFET, the way I have written here, between D1 and S1, the voltage dependent current source. The current will flow in response to the operated gate voltage, right? So therefore the current is flowing from drain to source, right? This from drain to source, right? So I should represent it by drain to source, right? This is GM2 VGS2, GM2 VGS2, and parallel to this there will be a resistance R02. In parallel to this there will be resistance R02. Okay, and so at the here this output node, right? Whatever the capacitance is there at this node, all these equivalent capacitance put together, I will represent it by C0. Okay, but here so this is a if you represent this node as X here, if you represent this node as X, okay, so this is GM2 VG2 S is now X. So it is VG2 EX. Am I right or not? But what is VG2S? Actually VG2 minus VS2, right? So that VG2 is 0, right? So it is just like it's VG2 minus VS2. S2 is X here. This is 0, so it's a minus VS2 or minus Vx. Am I right or not? So if you permit me, I will write this VGS2 as minus Vx. Am I right or not? So this is minus GM2 Vx, minus GM2 Vx. Minus अच्छा नहीं लगता. Great. What is your name? Snigdha. Okay. So okay. So this is my GM2 Vx and R02, right? R01, and that's all. This is what is possible equivalent circuit for the cascode. Now what I have to do? Same again, KCL I have to do, and then I have to evaluate. Ultimately I have to evaluate the transfer function. What is the transfer function? V naught by V in I have to calculate. So little bit of math you have to do here. I am now ignoring this math because it takes time. So we'll focus more on the concept. So if you evaluate all that, probably you will get it as this is the Vx here, and then substitute that, and ultimately you will get V naught by Vi is A1 A2 by 1 plus blah blah blah. You will get. Okay, this is the actual total transfer function, and if you assume that SR01 CDG is small as compared to A1, that is for the frequencies at which SR01 CDG is small, right? Omega is frequency and CDG is of the order of the femtofarads obviously. So therefore for those frequencies I can safely ignore. Then I will say that this is simply equal to A1 A2 by blah blah blah, right? Again, when omega is 0, S is equal to J omega, right, and omega is equal to 0, what is a DC gain is simply A1 A2, what we have already derived, right? So this is and also what you can just now think is R01 is approximately equal to R02, and 1 can be ignored as compared to A2. Then this is A1 A2 by 1 plus SR01 C0 A2, right? So if you try to evaluate the this one, the bandwidth, right? If you try to evaluate the bandwidth, what happened to bandwidth here? Bandwidth is equal to omega is equal to 1 by R01 C01 into A2, 1 by R01 into A2. Earlier bandwidth was 1 by R01 C01. Now DC gain is multiplied by A2, whereas bandwidth is reduced by A2. This is 3 dB bandwidth. But when it comes to the unity gain bandwidth, it is GM by CL. GM effective is GM1 only, so GM1 by CL only. Therefore, unity gain bandwidth remains the same. I have drawn here somewhere. Unity gain bandwidth remains the same as the single transistor amplifier, but the gain is increased by A2 times. But 3 dB bandwidth comes down. That I agree, right? So unity gain, for the same unity gain bandwidth, I am able to increase the gain by A2 times. Right? So this is what is the advantage of the cascode. Okay. So if you want to design the cascode amplifier, how do you go ahead? Initially, some specifications are gain is equal to, it will be given to you, and then gain bandwidth product is 100 megahertz. Our professor is there, Jairam, just to tell him that this also he has to do it for the 180 nanometers. Okay, tell him that. So this is the DC gain is given, and gain bandwidth product will be given to the unity gain frequency will be given to you, and then load capacity assumption some value. Now I have to start doing the design the cascode amplifier. How do I design the cascode amplifier? The question. So what I will do first of all, single trans amplifier do design. You design that. No, there also gain is given to you. Some load capacity is assumed. Therefore, what you have done there is for single trans amplifier, gain is equal to GM R naught, right? Gain is given to you, and then bandwidth also 1 by 2 pi R naught CL. So therefore, what you will do, CL is given to you, bandwidth is given to you. Therefore, you can calculate what is R naught. Once you calculate, because bandwidth is 1 by 2 pi R naught CL, CL is assumed, bandwidth is given to you, R naught you have calculated, R naught is equal to 1 by lambda ID. Therefore, you know R naught now, R naught 1 by lambda ID, lambda is known to you, ID you will calculate, you got the ID now with you. Gain is given as a specification, gain is equal to GM R naught, already R naught you have calculated. So gain is given to you, calculate GM. GM is equal to square root of 2 ID mu C ox W by L. So already ID you have calculated in the gain expression, in the GM expression, right? So simply you substitute, already GM you know, ID you know, and therefore you W by L you have to calculate, right? So it is not VGS, it is a W by L, right? That's all, design is over. So similarly for the cascode, how do you do that? For the cascode, how do you do that? For the cascode now, these are the specifications, right? So you start moving now, stating that don't just follow this, I just now make slight changes here. So gain bandwidth the product is given to you. Gain bandwidth product is given as specification, it is GM by C, GM by C. So GBW is given to you, it is a GM by C, C is total load capacitance. So you know CL and you know GBW, and try to calculate what is GM, right? So you can calculate what is GM1. Once you calculate GM1 and I know the gain is equal to what? I am assuming that transistor for M1 and M2 both are having the similar GM and R naught, right? Then the gain is simply GM1 R naught 1 into GM2 R naught 2, right? So the total gain is given to you. So 2500 is equal to GM1 R naught 1 into 1 plus GM2 R naught 2, right? Or if I assume that GM1 is equal to GM2 and G naught 1 is equal to G naught 2, then it is simply A into 1 plus A, right? Therefore, I can calculate what is A from here. Once I know what is the A here? A corresponds to the intrinsic gain of each of the transistor. Intrinsic gain of each of the GM R naught of each of the transistor. So once you know GM R naught of each of the transistor, you know, and for the lower transistor already you have just now seen that GM1 by C, right? What is the GBW? We have already calculated G1 by C. From the GM1 you already calculated. But you know GM1, and you know what is the GM1 R naught is equal to this. So from that you can calculate what is R naught 1, right? So you can calculate what is R naught 1. Okay. So once you calculate R naught 1, you need to follow this. You can just simply R naught 1 is 1 by lambda ID, R 1 by lambda ID. You know lambda and R naught, you know that from that ID you can calculate. So once you calculate ID here and use that expression here and calculate W by L. So the same W by L for both the transistors. So cascode design is also over, right? So what you have done for the cascode design? Let's recapitulate. What is the specification given to you? Gain bandwidth product is given to you, which is GM1 by C. C is assumed, so gain bandwidth product is there, is GM1 by C, therefore GM1 you calculate. Once you have done that, what is the gain here? Gain is equal to, it's also a specification given to you. So gain is a 2500 whatever is gain given to you, and you know the gain is equal to, I said that it is a 1 into 1 plus A2, right? Assuming that A2 is equal to A1, the GM R naught are the same for both of them. A into 1 plus A, equate that and try to get what is A. Right? Once you know A is equal to GM1 R naught 1. Already GM1 you have calculated, substitute that. Right? So you will get what is R naught 1. And I know R naught 1 is equal to 1 by lambda ID. I know lambda, therefore I will calculate ID. And once I know ID, I know GM value. GM1 already we have calculated from the gain bandwidth expression. GM is equal to square root of 2 ID mu C ox W by L, right? Therefore, I know ID, I know GM, and I simply calculate W by L1. W by L1 is same as W by L2. Khel khatam, dukan. Right. So this is the story of cascode. Okay. And let's try to move towards you have patience. Should I close? Huh? So, what is time? 6. It's your choice. Pardon? We can't say, but then whenever you say stop, I'll stop, that's all. Okay? Whenever it's saturated. Okay. So very quickly, let's try to see. I'd like to mention here one thing. This is a simple common source amplifier. The question here is, actually I should have dealt in the beginning itself. If you want to design the amplifier, then which region you are supposed to bias is the question. In which region you want to bias? If you want to design the amplifier, in which region you want to bias the transistor? You know that there are 3 regions. What are they? So obviously, I think you will not prefer cutoff region. Right. So what is left over is cutoff. So sorry, saturation, linear region. So don't say active. I never said anything active, reactive. So I don't know what is active, right? So linear region and saturation region. Which region do you prefer if I want to design an amplifier? Is the question. Snigdha says linear. Constant, I want to amplify, you know. So how do I do that? Then linear. Huh? So quickly change. Huh? In which region you want to know the bass? Huh? Saturation. Why? Because you are saturated. Huh? In which region you want to bass? Why? Constant current, but what you want to amplify it. If the current is constant, you can't just do that, no? Right. So okay. So let's not. Already you are exhausted. When you want to, I think that will be answered a few minutes later. Let's say to first look at this. Now let me try to consider this circuit here. What is happening? The input voltage is varying here. Then now I want to plot the output voltage. Very quickly, what is going to happen? As the input voltage is greater than threshold voltage, till there is a threshold voltage, what happens? This fellow, Arey bhai sahab, when the input voltage is less than threshold voltage, transistor is cut off. There is no current. Wherever there is a flat saturation, there is nahi hai. Right. So here, when the input voltage is less than threshold voltage, there is no current. No current is flowing. Vout is equal to VDD minus ID RD. Vout is VDD minus ID RD. ID is 0. Right. So potential is only VDD. So it's a VDD is there. And now what happens? When the input voltage is greater than threshold voltage, then some current flows, therefore there is a drop, ID RD, and therefore Vout is equal to VDD minus ID RD. Then as the input voltage is greater than threshold voltage, the current starts increasing, therefore voltage drop ID RD also increases, therefore Vout starts decreasing. Right? So Vout is equal to VDD minus ID RD. Since ID RD is increasing, Vout should decrease. Right? So Vout keeps on decreasing. But in this region, transistor will be in which region? I don't know. During this portion, transistor will be in saturation or in the linear region is the question. Immediately after the cutoff, transistor will be in which region? Transistor will be in which region? Immediately after the cutoff, will it go to saturation? Linear region. So, how do you say that? There is saturation or cutoff or linear region, whatever. What is the condition? Pardon? Linear, who said linearly? I didn't say anything. It all depends upon which region it is, right? So in which region, how do you judge is basically VDS is greater than VGS minus V threshold, then transition is saturation. If VDS is less than VGS minus V threshold, this is linear region. So here VDS is V out only. In this portion, VDS is almost equal to VDD, it is closer to VDD, right? And VGS minus V threshold, it is just above threshold voltage. Let us say threshold voltage is 1 volt, applied voltage is 1.1 volt. VGS minus V threshold is input voltage is 1.1 volt, threshold voltage is 1 volt. What is VGS minus V threshold? Input voltage is 1.1 volt. That is VGS is 1.1 volt. Threshold voltage is 1 volt. So what is VGS minus V threshold? 0.1. So it is such a small value. VGS minus V threshold is such a small value, whereas VDS is closer to VDD. So which is larger? VDS is larger or VGS minus V threshold is larger? VDS is larger or VGS minus V threshold is larger? VDS is larger. When VDS is larger than VGS minus V threshold, transistor will be in which region? Saturation region. Therefore, the transistor here will be in the saturation region. Right? So as you keep on increasing the input voltage, the current keeps on increasing, therefore drop keeps on increasing and output voltage keeps on decreasing. So VDS keeps on decreasing, therefore that means I am always comparing VDS with respect to VGS minus V threshold. Now VDS is decreasing and VGS minus V threshold, because VGS is increasing, this value is increasing, right? So this value is decreasing, this value is increasing. For a specific value, this will become equal, and further this may go higher. VGS minus V threshold will go higher as compared to VDS. Then the transistor will enter into linear region from saturation. So therefore, for a specific value of the input here, the transistor enters into the linear region. So that's all. Now why should I worry about all this is because whenever I want to evaluate any GM or blah blah blah, in which region it is I should know, then only I will apply the corresponding expression for the current, right? So this is what is possible equivalent circuit here, and I can calculate the gain. The gain is equal to minus GM V1 into RD is the output voltage. So divided by input voltage is a V in. So this simply gain is minus GM1 RD. Okay. So now you can in the different regions you can calculate what is the gain here. Okay. I don't want to. So as I said, now when it enters into the deep triode region, when it enters into the, because you keep on increasing the V in, then it enters in deep triode region. Then I can replace the transistor by resistance also, right? So I can it just appears like this. So it appears like how it appears. Just see here, it appears like a transistor in the deep triode region. This is like a resistor. This is like a resistor here. It is just a voltage divider. Okay. Just a voltage divider. Okay. So now, in the place of the resistor, the gain of course is all the time we calculate GM minus GM RD. Okay. Now let me try to just now see. Therefore, if the resistor in this mode I can it is a voltage divider I said. Then VDD by R on plus RD into R on. So substitute what is R on here. This is no big deal. And this is for the saturation region. Now what I would like to do is in the place of resistor load, I will try to replace the current source the way we have done earlier and try to calculate the gain, which we have already done it. Okay. Now there is an interesting experiment which we would like to do it. What we would like to do here is by varying the input voltage, we would like to plot GM. By varying the input voltage, we would like to plot GM. So the same circuit which I have done, resistive load. When you keep on doing that, when the input voltage is greater than threshold, less than threshold voltage, current is 0, GM is 0. When the input voltage is greater than threshold voltage, what will happen? Transistor is entering into which region? Immediately, we said it is a saturation region. Further circuit, there is no hard and fast rule. That circuit is all. So then I have to take the expression of the GM for the transistor which is in the saturation. What is the expression for the GM which is in the saturation? GM is equal to, you have already calculated, right? ID is equal to half mu C ox W into VGS minus VGS whole square, and dou ID by dou VGS is equal to mu C, what is that? 2 gets cancelled, the mu C ox W into VGS minus V threshold. Mu C ox W into VGS minus V threshold, so that means it is simply linearly varying with the VGS, right, or Vn. So as Vn is increasing, the GM is varying linearly, increasing with respect to input voltage as it increases. But when it reaches this point here, there the transistor is entering linear region, therefore I have to use the corresponding expression for the linear region. Then again GM I have to calculate for the linear region. In the linear region I have to write the current equation again. ID is equal to mu C ox W into VGS minus V threshold into VDS minus VDS square by 2, and then try to dou ID by dou VGS to calculate, then it becomes mu C ox W into VGS minus V threshold into VDS. You will get it and do it, right. So that means it is now proportional to VDS. GM is proportional to VDS. So but what is happened to VDS here? As input voltage is increasing, VDS is decreasing, no. Therefore GM keeps on falling. GM keeps on falling, right. So now the question that I posed earlier, that is, in which region should I bias the transistor if I want to use it as an amplifier? That's the question, right? Right. So if you use in the saturation, what is going to happen? The GM is increasing, but in the linear region, it is falling. It's falling. No one wants that. Sensitivity should be low, right? GM is sensitivity, and therefore gain is GM or not. And therefore, you don't want that to happen, and therefore, obviously, the preferred reason is saturation. Not only that, actually, what we would like to do is, if you try to bias it in the linear region, the current is also a function of VDS, because in the linear region, current is also a function of VDS. So, but you would like to have the variation in the current to respond to only applied signal variation at the gate, that is at the input, but you don't want the current to vary due to some voltage variation at the output, due to some other reason. If load varies, that also varies. I don't want that, right. So when just like you are in the class, and the teacher always wants that when he speaks, then all the class should listen, and then, right. But if he speaks and the others also speaking, then ultimately chaos. You don't want that, right. So therefore you want that this current should vary only in response to signal variation, but not to that load varies due to some other something else is also varying. You will never know the variation of the current is due to the variation of signal or something else, and therefore, but always we feel that, oh, output is varying, oh, because the input is varying, output is varying. But if it is in the linear region, even if the output voltage varies due to some other, that also varies. That is a wrong interpretation. Therefore we feel that the current should only dance to the tune of signal that is applied at the gate, right. Understand? Therefore the transistor should be in which region? Saturation. Those are the two regions which you can just attribute, right. Alright, so you can always calculate, right. So how do you maximize the gain is the question here. So she has already given a signal to signal, the signal that is already saturation, very good. I am happy that we learned a lot of things. Let's try to tell that now, close it. Is that you are telling? So gain is equal to, how do you evaluate the gain here? So again already I have just GM RD. So what I have the minus GM RD, GM is my square root of 2 mu C x W by L into ID, actually ID is there inside. So the ID, so this is actually gain. What is gain is minus GM RD, right? What is GM? GM is equal to square root of 2 ID mu C x W by L, right? And RD I am writing some trickish fashion. RD I am writing it as VRD is ID RD. VRD is ID into RD, right? So what is RD? How do I write RD as ID RD by ID? ID RD by ID. I can write ID RD is VRD. So VRD by ID. But under एक ID था, therefore it gets cancelled and then it becomes square root of ID here. Now this is the gain expression. Now look at this expression. I want to maximize the gain. How do I maximize the gain is the question. How do I maximize the gain is the question. How do I maximize the gain? So by increasing W by L, or decreasing current, or increasing this, all things are possible, right? But that's an electa. If you want to just go for increasing W by L, what happens is the capacitance, parasitic capacitance also increases. Therefore, speed is at stake. If you want to increase VRD, then power dissipation is at stake, right? So because IDRD increases, then dissipation, power dissipation increases, right? So therefore, there are so many trade-offs are there. If you want to maximize the gain, there are so many trade-offs are there between the gain, bandwidth, and the speed, whatever it is, right. So that you have to keep in mind, and I don't want to. So what you understood now is that if you want to design an amplifier, there are so many things you have to, a lot of trade-offs are there. So कुछ तो therefore जब आप कुछ you want to पकाना चाहते हैं, you want just to prepare something, then you want to make it balanced. Is very difficult, right? You want to have some taste, right? You want to have some sour taste, then probably something else will do, right? So add salt or this or that. Then BP patients are there, then you don't want to add BP, and then what happens? So therefore these all are the trade-offs. So there is a now coming to this one. This is called, here gate and drain are connected together. We call it the diode connect transistor. Is there a diode connect transistor? Here very quickly we'll try to, without going to math, we'll try to say that this transistor, whether it is in saturation or not, is a question here. Why you want to look that is, I'll tell later on. So because gate and drain are connected together, in which region it can be in the sense all the time here what is VDS? VDS is equal to VGS here. Am I right or not? VDS. This is the drain. Drain. This is drain. This is the source. So VDS is same as VGS because drain and gate are connected together. So what is the condition required for the transistor to be in saturation? VDS should be greater than VGS minus threshold. So since VDS is equal to VGS, then I can always say that transistor is always in the saturation. When this fellow is in saturation, therefore can I use it as a current source is a question. Can I use it as a current source or not is a question? Who? Oh, this fellow is call him. Video time is over. I want to go. So not you. आपके पीछे वाला. He is there outside. He went there with his mobile.
Sir, good evening, sir. I can.
వీడియో వాళ్ళ ఫోన్ చేశాడా? వీడియో అని ఫోన్ చేశాడంట. అంటే అవర్స్ అయిపోయినాయని లేదా? ఓకే సరే. ఇంకా బాగుతూనే ఉన్నాను. ఓకే రైట్. Since they asked that a simple is a common source amplifier. For the sake of simplicity, we are trying to connect that an ideal current source. Now, what I am going to do, DID is, I know the current in a MOSFET is a function of two variable voltages. What are they? One is VGS, another one is VDS. So current is a function of, therefore DID, small change in the current is a function of dVg and also the function of dVg. Therefore, dou by dou dVg plus dou by dou dVg. So by definition here, I can write dou ID by dou Vg is equal to G. Right? So and dou ID by dou Vg is G. So dou Vg by dou ID is R. Okay. Which is reciprocal that is G. So we can write the differences here. Now what I can do? So, but I know since I connected constant source, DID is equal to 0. I'll start writing the equation. DID is equal to 0. 0 is equal to, now whatever the earlier I put there, dVd and all, I'm trying to replace it by small. I'm trying to replace it by, this is dou ID by dou Vg gm. This is gm. And this dVg, I'll write small letters Vg. Vg is actually Vi. Yes. And this is a G naught. And this is V small. Okay. So if you want to value the gain, what I will do? Gain is equal to V naught by gain. Right? So it is essentially take these two things this and that set, and then V naught by V is equal to minus Gm by V naught or minus Gm. And so I can write, don't read too much into these equations which I have already seen. So this is ultimately gain expression, and current is half mu C of square. Other parameters are simply taken on the parameters. Okay? So we always see that the Gm can be expressed in three different ways as a current batch, voltage pattern. So now if you want to evaluate Now if you interest in evaluating the gain in all the three modes, etc. Voltage bias, current bias, so technology. All the three types probably you can evaluate the gain. But evaluate the gain, then you should know what is GM in all the three modes, right? And also you should know what is R naught in all the three modes, or P naught in all the three modes. So for which case what we do? So this is a all the three modes we can evaluate the what we call GM, G naught and the P. Okay. So this is G naught is equal to, already we have seen that is under lambda ID, right? So this is exactly the same, and G naught in all the three modes is one mode that is here, and so for example this is calculated in the voltage bias mode, and so this is gain, right? Therefore, similarly, you can evaluate in the current bias mode. Math, if you do, will discuss. There's no point in doing math here. Just take it down. So, see, what is the way to do? We calculate G naught. How GM is calculated in GM is expressed in terms of what is it? Voltage bias mode, the current bias, and the current bias. And therefore, in the current voltage bias mode, GM is there, G naught is there. Multiply GM, G naught, you get K. Same is the case for the other two modes. When you try to do that, in the current bias, you find that the gain is proportional to the square root of the area. Square root of area. Okay. Okay. So now what we try to do is try to apply case in this one equivalent circuit. So far what we have done? So far what we have done is we have ignored the capacitances and simply we are calculating the gain in GMR not we are having. This is not the case. There are capacitances existing, therefore you have to take the constant term. So what are those capacitances here? The capacitances are the gate and source, this capacitance, the gate and drain, this capacitance. So here are this capacitance, right? So apply KCL here. Apply KCL now, you do this math and that's from the I'm trying to go faster. So this is a VI, this is VI, this is V0, right? So VI minus V0 divided by 1 by CGDS, okay? That is that becomes a CGDS into VA minus V0. This is the one current here, right? And the leading current here is GMVI, so minus GMVI. And what else? The other leading current is V0 divided by R0 and V0 divided by 1 by S C0. Okay. So if you solve, you will get the gain as this.
So you can also verify that at zero frequency SC is equal to j omega, right? So omega is 0, simply this all will go and minus GM or not, right? So I can write my gain as in terms of C total. This is what is the gain here, and that is A naught into the GM or naught is A naught. I have put here. I will try to express this way. Okay. Now what I would like to just make an assumption is that this omega CGD is far for the frequencies omega CGD by GM is far less than 1, right? And it is not a, I am not doing any violation here. What I am trying to do is omega CGD by GM is far less than 1. That is what I am just because GM is pretty larger generally. GM is larger, and I am trying to consider those frequencies for which omega into CGD by GM is far less than 1. Generally it is the case, whatever is because I said GM is pretty large and CGD is of the order of the femtofarads. So already out of the order of femtofarads and divided by large GM try to put here. Therefore I try to get here that value will definitely be small far less than 1. So I can just now ignore for those frequencies, and then this is approximately equal to this here. So therefore gain bandwidth, this is the gain here, and the gain bandwidth product if you want to evaluate, because this is the gain, and this multiplied by gain bandwidth product, right? So before we go to that, please try to see that this describes the frequency response of a system with one dominant pole. There is only one dominant pole. What is that pole here? The pole is
if you want to evaluate omega is equal to 1 by r naught C total, right, 1 by 2 by r naught C total, right. So therefore the bandwidth is given by 1 by r naught C total, and the gain bandwidth product if you want to evaluate, gain is GM r naught multiplied by bandwidth 1 by r naught C total, so which is simply GM by C total, right. So what is this? This is what is gain bandwidth, in the sense unity gain frequency. This is the frequency for which the gain falls to unity, right, or the gain output becomes equal to input here, right. So this is what is the gain bandwidth product here. So as frequency increases, this becomes unity. Okay, well, okay. So now, so the maximum possible cutoff frequency occurs for an unloaded amplifier, because C total keeps on increasing when you try to add more and more load, right. So C total is equal to obviously how can I write here? There where the capacitive load is entirely due to the device capacitance itself. So therefore C total is a function of the device capacitance is proportional to W. Right. So therefore I will write GBW maximum is equal to GM by C total. I said in the place of C total I am writing it as the function of W, some zeta into W. Okay. Now GBW maximum you can also calculate as K dash VGT by, this is for all the three styles you can calculate, for all the three styles you can calculate. Please make a note of this slide. You have to change the equation numbers, all these things you have to remove it. So this all is the all the three different styles. This is what is the GBW. Okay. Here you can tabulate all this. You can tabulate all whatever for all the three styles, right? What are the three styles? Voltage base. The voltage base, the free design variables are WL and VGT, and for the current base WL ID, and for the other base it's L, VGT and ID. You can calculate GM, G0, A0, GBW and GBW maximum, whatever it is. Right. So now what is that? Why we have plotted all? Why we have actually tabulated all this is the question here. So one important observation we try to draw here. So if you want to evaluate the gain multiplied by GBW maximum, right, then you can find that it is ultimately gain into GBW maximum is some 2k dash by alpha, all this, right. Don't read too much into all the what is a lambda, all this is just a function of technology parameters. So the observation is that nowhere your there is no, it's not a function of the voltage, it is not a function of the current, it is not the function of W or L, whatever. That means that when you try to evaluate the gain and GBW maximum product, this is fixed for this topology. If I want to improve it, I can't do it. Nothing is there in my hand. Voltage is not there, current is not there, W is not there, L is not there, right. Therefore what it implies is, if I try to increase, if I want to improve this performance of this topology, I can't. I am pushed to wall. I am pushed to wall. Therefore the only way which is left with me is change the technology, right, or otherwise go for another topology. For this topology common source I can't do anything more. Not only that, in the common source amplifier you can just now also see in the common source amplifier you can also see that between the gate and the drain there is CGD is there, right. This capacitance CGD, right. Now where you are taking output here, I am trying to take output here, and this is the input, but the output and the input there is an impedance which is in terms of capacitance here. Try to recall the Miller theorem that in an amplifier when there is an impedance between the output and the input here, that can be replaced by how? At the input, I will remove this feedback. At the input it can be seen as it can be seen as, if the impedance is Z here, then it is seen as Z by 1 minus AV, Z by 1 minus AV. So when Z is here, what? 1 by CS, 1 by CGD. So 1 by CGD, This is the Z which is connected in the output and the input here. So that can be written as Z by 1 minus AV. So Z is equal to 1 by CS or CGDS, okay, into 1 minus AV. 1 is small as compared to voltage gain, so it is AV, right. It appears that the CGD is multiplied by gain times and is appearing at the input, right. So that is actually, that may cause the frequency response to be hampered. So what that means is, if I try to this is the voltage gain and this is the frequency, right. If I try to increase the gain, right. So what is happening? This capacitance which is it's encountering seems to be large, right. So therefore the corresponding pole moves towards the origin, right. So I can say that this unity gain frequency is coming closer to the origin. So available this gain bandwidth is decreasing, right. So the larger the gain, the smaller the bandwidth it is, right. So therefore for this given technology I can't improve anymore. Now I want to see that for the same unity gain bandwidth, that is earlier it is like this, right. So this is here, I want to go here, then it is. But if I want to increase the gain, but I don't want to change this unity gain frequency. I don't want to change this unity gain frequency. For the same unity gain frequency, I want to get a larger gain. Then what should I do? That is, I want to get a larger gain here. So for the same unity gain frequency, I want to have this. Okay, I want to get a larger gain for the same unity gain frequency. I can't do anything here, but I should think of a solution. So whenever there is a problem, then if you want to look at the solution, then immediately what we have to look at is who is the culprit, who is causing the problem, right. Who is the culprit and who is causing the problem? Who is the culprit? The culprit is this fellow. This capacitance is between the output and the input, the capacitance CGD is there, right. So that fellow due to the Miller, it is getting multiplied by gain terms actually. The larger the gain, the larger you are increasing W, and therefore the larger the C, and therefore actually the C is getting even multiplied by gain terms. So therefore what is to be done is, since between the output and the input the capacitance is there, so somehow you have to resolve it. So probably if you don't take the output from here, take somewhere else here and isolate, that is isolate the output node and the input node. Isolate the output node and the input node. Isolation in the sense, who will come to our rescue in the MOSFET technology or the circuits here. No one else come to our rescue, only another MOSFET only will come to our rescue, right. So therefore what I will do, I will use another MOSFET and I will try to isolate what? I will try to isolate output and the input node, right, because output and input node, if I am taking output here, then this CGD is between the output and input, it is there. I will not take output here, I will try to put another MOSFET here and try to take output from here, right. Then I am successful in isolating the input and the output node, right. So this is what exactly I can see, that I have isolated the output node from the input node by connecting another MOSFET. This is the cascode topology. So I am trying to get rid of the Miller effect, and therefore I want to improve the performance. Okay. So here you can analyze once again. Okay. So remember, these two transistors are in series, therefore current through both of them are same, right. We will analyze it with a small assumption. Let us assume that there is a fictitious transistor, because here what is happening, please remember, here signal is applied here only, here I am giving only DC, okay. Therefore I can view this as a single transistor, a fictitious transistor, UHA generated transistor, and which is taking input from the gate of the, this is called driving transistor, because this fellow is being driven by the input signal. This fellow is not driven by input signal, but there is a, what is this voltage? DC voltage. This is a DC voltage to keep this in saturation. Okay. Okay. So therefore, this is DC voltage, all right. Now what we would like to see here is, when you try to treat this as a single fixed transistor, and input voltage is from at the driving transistor, and output is being taken here. Okay. So this is single transistor. Now dou ID by dou VG1 is going to give me the transconductance of that single transistor, GM effective we call. This is for the, not for the this transistor, this is for the circuit. The circuit is viewed as if a single transistor, input here, output there. Dou ID by dou VG1 is the effective transconductance, GM effective. Similarly, dou ID by dou VD2 is the effective conductance, G0. Okay. Well, so again same story. This DID is any current is a function of what? Transconductance, as a function of the gate voltage and the drain voltage. I am viewing these two as a compound transistor, where input is being taken from VG1, therefore GM equivalent into dVG1 plus G0 equivalent into dVD2. Right? Now GM equivalent is equal to dou ID by dou VG1, but by dVD2 is equal to 0, because I want to see the variation in the current only due to the variation in the VG1. So VD2 I am trying to mute it. Right. Similarly, G0 equivalent if I want to calculate dou ID by dou VD2 when dVG1 is 0. Right. So therefore, I can now write dVds2 is equal to dVd2 minus dVs2. VD2, I know that the source of this fellow, see this source of this transistor is the same as the drain of this transistor. So Vs2 is equal to Vd1, Vs2 is equal to Vd1. Am I right or not? Huh? Am I right or not? Vs2, this is transistor M2. Vs2 is same as Vd1. Not convinced. This is the source. S2 and D1 are connected together. S2 and D1 are connected together. So the obviously Vs2 is equal is same as Vd1. Vs2 is same as so Vs2 is same as Vd1, and same as again we have what is the why actually what is this 0 here, because dVd2 minus dVs2, right? dVd2 we have made it as 0. Why dVd2 is made as 0? Because we want to calculate GM effective. When we calculate GM effective, what are we doing? dVdt is 0. Only variation due to the voltage at the gate. The current is only due to the applied voltage at the gate of the M1. So therefore this is 0. Now dVgs2 is equal to dVg2 minus dVs2, but dVg2 is also 0. Why dVg2 is 0? Why dVg2 is 0? dVg2 is 0 because you are right, you are there. What is your name? What is your name? Rishi? Trisha. Okay. Good. Even if it is winter, you are working. Actually, you are supposed to work only during rainy season. So, this is. You are right. Tell me. You are right. It is the DC voltage. It's not difference. It is a DC voltage. The DC voltage, therefore, signal I am not applying there. Therefore, delta change whatever 0. There won't be any change there. Am I right or not? So this is dVg2 is or small vg2, it is 0. Right? All the time it is 0. all the time it is 0, right. So, therefore, this is 0 minus dVs2, dVs2 is again dVd1, right. So,